This is the solution for question 2 of homework 2. The question we are given a communication system, something similar, where we are sending data xk to a noisy channel and receiving xk plus 1. So if we look at it as a change in states, initially we are given that probability of the initial state being 0 is 0.2 and probability of the initial state being 1 is 0.8. So the probability for the various changes in the states are given. We are asked to find the probability that the next state, which is x2, is 1. So p of x2 can be 1 if initially x1 is 0 and it changes to x2 equal to 1, or if x1 is 1 initially and there's no change in state and x2 remains the same. So using total probability, p of x2 equal to 1 is p of x2 equal to 1 given x1 equal to 0 into p of x1 equal to 0 plus p of x2 equal to 1 given x1 equal to 1 into p of x1 equal to 1. Substituting the values, we get 0.64, and here p of x2 equal to 0 is just 1 minus p of x2 equal to 1, but this is the formula for it. So I've written it so that I can show you the matrix notation. So this change of state can be looked at this way. So the probability that the state k plus 1 is 0 and p of the probability for the state k plus 1 to be 1, this vector is equal to the initial state xk multiplied by the transition matrix, or the probability of the error, or the probability of not changing states. So this matrix over here is always a constant, which values are given over here. So this matrix notation is very useful for solving complicated questions of this type. So for the next part, we are asked to find probability that x3 is 1. So using the matrix notation, since we only need probability of x3 equal to 1, we only want this part, so we do this multiplied by this. We don't need this one for now. So probability of x3 equal to 1 is this one, this vector multiplied by this vector. So substituting the values, we get 0.592. Now the next part, we are asked to find p of x1 equal to 0 given x3 equal to 1. So this can be done using base rule. P of x1 equal to 0 given x3 equal to 1 is p of x3 equal to 1 given x1 equal to 0 into p of x1 equal to 0 divided by p of x3 equal to 1. So but p of x3 is dependent on x2, which is in turn dependent on x1. Therefore p of x3 equal to 1 given x1 equal to 0 can be represented as p of x3 equal to 1 given x2 is 1 and x1 equal to 0 multiplied by probability of x2 equal to 1 given x1 equal to 0 plus probability of x3 equal to 1 given x2 equal to 0 and x1 equal to 0 multiplied by probability of x2 equal to 0 given x1 equal to 0. This is because we are given that x1 is 0 but x3 is dependent on x2, which is in turn dependent on x1. So we are fixing x1 to be 0, but x3 equal to 1 can happen when x2 equal to 1 and the state does not change, it remains the same, or x2 equal to 0 and there's a change state transition and x3 becomes 1. So accounting for those, we get this equation. Substituting the values, we get 0.17. Now in the next part, we are asked to find limit n tends to infinity probability of xn equal to 0. So now back to the matrix notation. So since this part is always a constant. The values are given over here: 0.6, 0.4, 0.3 and 0.7. Now p of x k plus 1 equal to 0 and p of x k plus 1 equal to 1 depends on xk multiplied by this transition matrix, but xk itself depends on xk minus 1. So xk can be represented as p of xk minus 1 equal to 0, the vector p of xk k minus 1 equal to 0, and p of x k minus 1 equal to 1 multiplied by this transition matrix. So if we expand that, p of xn equal to 0 and p of xn equal to 1 is dependent on the first state multiplied by the transition matrix whole power n. So now we are supposed to find this limit n tends to infinity of this part, only this part. So how do we do the value, how do we calculate a power n or the matrix power n? So in linear algebra is a standard result, the diagonalization of a matrix. So let us take a matrix A, the transition matrix A equal to V lambda V inverse, where lambda is the eigenvalue vector and V is the eigenvector matrix. Now calculating the eigenvalues is simply substituting the matrix values in this formula, det of A minus lambda I equal to 0. So we have two possible eigenvalues, which are lambda equal to 1 and lambda equal to 0.3. So therefore this lambda will be 100.3, and so this basically we are doing this because a power n can be represented as V lambda power n V inverse. This is the standard result. So we are supposed to find V lambda and V inverse. So we have found lambda. Now coming to V is the eigenvector matrix. So eigenvector is for each eigenvalue, the null solution for A minus lambda I is the eigenvalue. For finding the eigenvalue, we use this formula, A minus lambda I into V1 equal to 0. Let us denote V1 as x and y. Solving this set of equations, we get x equal to y. So any values x equal to y can be used as an eigenvector. For let us take V1 as 1 1, x and y are equal to 1 for easier calculations. Now this is the first eigenvector for lambda equal to 1. For lambda equal to 0.3, we get another eigenvector, which is solved similarly. Over here we get the solution y equal to minus 3x by 4. As before, we take x equal to 1, therefore y equal to minus 3 by 4. This is just to make the calculations easier. We can take any values. So we get the matrix V as 1 1, the previous eigenvector, and 1 3 by 4, which is the new eigenvector. This is the matrix V, and V inverse can be calculated, which is this value, this matrix. Substituting in that formula, we have A equal to V lambda V inverse, this multiplication of these matrices. Since A power n equal to V lambda power n V power minus n, we can denote it as in this way. A lambda power n is simply 1 power n 0 0 into 0.3 whole power n. Now back to the question. Limit n tends to infinity, p of xn equal to 0 and p of xn equal to 1 is limit n tends to infinity, the initial state, multiplied by the transition matrix whole power n. So substituting a power n over here, we see that limit, the only places where n is present is 1 power n and 0.3 power n. So as limit n tends to infinity, 1 power n is 1, but limit n tends to infinity, 0.3 whole power n is 0. Therefore our matrix becomes 1 0 0 0. So first multiplying these two and then multiplying the result with this matrix, we get this final result 0.2, 0.8, 4 by 7 into this. Since we only want the probability of xn equal to 0, we only take the first part, which is 0.2, 0.8 multiplied by 3, 7, 3 by 7. So therefore limit n as to infinity of xn equal to 0 is just a multiplication of these two vectors, this vector and this vector. So the final result comes out to be 3 by 7.